Okay, I believe this was the slide we finished last day, right? This was the next one we were going to do? Okay.
Yeah.
So let's just do a quick recap of what we're talking about here. Our goal is to try to order and count the number of ways you can do things. Why would you care? Why is this relevant? Gambling. It's on the diploma. March Madness. She probably has the best point of all, but the best example I can give, though, is security. Right? The more number of combinations that are possible, the more secure something is. Right? Now, one of the best ways of trying to keep track of it was called a sample space, where you literally write out every possibility. My goal over the next 3 lessons here is to try to get away from writing them all out, so that we can actually just figure out like little tricks as to, well, we just need to times these numbers or add these numbers to each other. Okay? So here's another example here. You're playing baseball, and you have 9 people on your baseball team. Do you guys know how many people you need in a batting order? You need 9. Okay. So what we've got going on here is we have 9 people, and we need 9 of them to go bat. How many different ways could the coach arrange his batting lineup? So, if you want to write it out kind of the long way, that's the short way then. Okay. So the short way is 9 exclamation point. Why? You call it a factorial, by the way. Explanation mark. You call it factorial. That's the way you say it. Yeah. The reason why is it's 9 times 8 times 7 all the way down till the last person really you have no choice on. Now, I didn't really want this example so much for the first one. It's actually the second one. This is a great example of, in sports, let's say there's 15 people trying out for a team, but only 9 make it. We're having cuts, guys. Someone's getting cut. That make sense? Probably me. So there's 9 people who make the team. There's, stay with me, please. 9 people make the team. Out of 15 total, 6 are getting cut. Well, a fast way of writing this is 15 factorial over 6. Let me show you why. For the first spot on the team, there's 15 people who can make it. For the next spot on the team, there's 14 choices. Why does it go down? Yeah, because once the person's on the team, that you can't put them on the team again, right? Once you're on the team, you're already there, right? So now I picked you, now I pick you, and you, right? So, but not everybody. Not everybody's making the team, right? So there's 5 people on the team, 6 are now on the team, 7 are now on the team, 8 are now on the team, 9 people are now on the team. We now have a team of 1, 2, 3, 4, 5, 6, 7, 8, 9 people. But do you guys get the point I'm trying to make here? Is that 6 people do not make the team. A fast way of writing this out is 15 over 6. Right? Now again, I don't care what the actual number is. I'm going to assume you guys can just find that yourselves. But this is the way you do that. Okay. Here's another really common example type. I'm going to start basic here. Let's say you have 7 people, and you need to line them up for a photo. It doesn't really matter that it's a photo, but you've got 7 people. Let's arrange them all. Well, the answer is 7 factorial. Because really, there's 7 people who could go in this spot, and then 6 who can go here, and then eventually you get to the last spot, and only 1 person goes there. So that's not really my point, though. It's actually the next 2 questions that are important. Here's a scenario. In the photo, Frank and Jill have to stand next to each other. And the silly example I use in everyday life is Frank and Jill just started dating. They are so in love with each other. Maybe you know people who are like this, where like they just don't leave each other's sides. Like they eat next to each other. These people who are like this, and so you're trying to take this photo, but like Frank and Jill will just not split up. They have to go next to each other. Does that make sense?
I still do that.
Yeah.
10 months.
Nice, good for you. So, anyways, the point is, how do you account for a little twist there where this is a requirement now that it can't just be 7 random people? So, let me show you how to do this with manipulatives first. I'm gonna grab a few items here, and I need someone to lend me their calculator. Actually, here you go. Okay. So here's 1, 2, 3, 4, 5, 6, and 7 items. Can you guys see them all here? And what we're going to do is, these 2 are Frank and Jill, and they just love each other so much that they have to be next to each other. So this right here would not be a valid arrangement because Frank and Jill are not next to each other. Does that make sense? So let me show you some possible valid arrangements. They could go here next to each other. That would work. They could go here next to each other, but they can't do that. Makes sense? So you know how that answer we just had for the first one was 7 factorial? The next answer is clearly going to be less than that. Does that make sense? Because of all of the 7 ways that we can arrange these items here, this one here is not possible. This one here is not possible, but that one now is where they're actually next to each other. Does that make sense?
All the senior girls volleyball, including Joan Baxter and Denise Perry, you should be heading to the gym. Also a reminder to all the other students, the girls play today at 1, 3:30, and 7:15. So if you have nothing going on tonight, please come and watch them play some awesome volleyball.
Okay, for those of you who are watching the video, I'm talking into my microphone now, I've got 7 items here in front of me. Here's what I'm going to do to solve the problem of 2 people who have to be next to each other. Treat them as one person. Okay? Because really, that couple that you know who never leaves each other, they basically are one person, right? So right here, there's 2 people in this put-together calculator, and we're just going to count them as one person now. Well, now, how many items are there? 6, yeah. So the answer is actually, it's not just that, though. There's one more twist we have to account for. It's not 6 factorial, but in theory, as this amalgamation of 2 people here, can't it go anywhere in this lineup, and now they're next to each other? I like doing this, though, because I want to put it in this order here. What you could have is go tape, then string, then Frank and Jill, but could you not also do it like this, where then it goes Jill, then Frank? See how that works? So there's actually 1, 2, 3, 4, 5, 6 items here, but this last one right here, which is really 2 items, it could go this way first, or it could go that way second. I used a really important word here. I used the word or, which means that you could do 6 factorial with, like, say, Frank before Jill, or you could do a second set of 6 factorials with Jill before Frank. So here's the best way of writing it. This is 6 factorial times 2. Show that with manipulatives one more time here. Right here, this was not a valid combination because they're separated, right? So the only valid combinations are where they're literally next to each other, right? Well, to make it simpler, why don't we just make them one person? They're effectively one person. 1, 2, 3, 4, 5, 6. But it could be Frank, then Jill, or it could be Jill, then Frank. Does that make sense? It is a different order, but they're still next to each other. So the way you solve a question with this sort of twist, actually I still need that actually, is you drop the number by 1. So rather than having 7 people, drop it by 1 and make it 6 people, but then you have to double it. Normally I haven't actually asked you guys to calculate these numbers here, but I'm going to need them for this one here to make a point. Someone talk about 7 factorial is? Oh, good question. So if you don't know how to put it in your calculator, here's a calculator. Type in 7. 50, 40. Okay, math. Go over to PRB, probability, and there's the exclamation mark there. Okay, so this one is 50, 40. Okay, before I type in the next one here, though, would it be logical that this number here, though, should be less than 50, 40? Because many of those combinations are reduced because this one right here is 7 people in a row, but it's not valid, right? So, what was 6 factorial times 2? Anybody get that? 1440. Okay, so this one's 1440. That makes sense. A whole bunch of the possibilities are out. That's actually the key to my last question here. So, this one right here, Frank and Jill love each other so much that they must be next to each other at all times. It's been 11 months later? Hey, Frank and Jill broke up. And now they can't be next to each other. Sorry, I didn't mean that to you. But Frank and Jill have now broken up, right? And now they have to be in the same photos. But here's the rule. They cannot be next to each other. We better separate them. Now, I'm not saying they have to be on opposite ends, although that is valid. But at the very least, there has to be a 1-person buffer between them. Does that make sense? At the very least. This would be a valid combo because there's 2 people between them. This is probably the best combo because they're on opposite sides. But even this would work, so long as there's at least something between them. Well, here's how you solve this question. If there were 5,040 ways in which there were like total possibilities, and there were 1,440 ways in which they are together, if you subtract them, this would be the number of ways in which they are not together. Because really, there's only two possibilities. Either they are next to each other, or they're not. So if we've just found all the places in which they are next to each other, subtract it from the total, and now you found the ways in which they're not next to each other. So 5040 minus 1440 is 3,600. This is a really common twist. Okay. I like to use, when I refer to it, I'll call it like the couple who breaks up kind of problem, just so you know what I'm referring to. So the first example is the couple who has to be together. Drop the number by 1, factorial it times by 2. The second example is if they've now broken up, take the total and minus the when they are together. That tells you when they're. Now you got this back. For anybody who watches this as a video later, I was using manipulatives, so maybe ask me to show you that if you feel you need it. I do to nobody. Okay. Talking to hypothetical people watching this video. Okay, here's another weird example. This one doesn't make sense yet as to why you do it, so just bear with me. But let's say that you had the Scrabble tiles P-U-P-P-Y, and I wanted you to rearrange those Scrabble tiles. Okay. How many ways could you rearrange them? Well, you might think, you look at the example and say, well, there's 5 tiles. So 5 tiles would mean 5 factorial. That's actually not the answer. Well, and it's not that either. This is where I need to show you some examples here. Let's just start randomly picking letters and rearrange them. Let's go with the Y first, and then say one of the P's, and then U, and then another P, and then I guess the last P. Okay, there, I've randomly rearranged them. So in a way, there were 5 choices for this letter, and then there were 4 choices for this, and then 3 choices for this, and then 2 choices for this, and by the time I got to my last choice, I didn't even have a choice. I mean, I did, I had 1 choice. But here's the problem.
There's 3 P's, so you
yeah.
can make the exact same thing.
If I were to rearrange those 2 P's right there and change their order, let me actually do this. Here, I'm going to select this. Oh, this would be good. Hang on a second. Just for the visual. So there's one there. And here's the second one here. If I were to select this item and change it with that one there and rearrange it around, is it actually different? Well, I know I colored them so I could see them, but does it actually spell a different word? No. And there is another twist I need to prep you for, is what happens if some of the items that you're referring to are literally the same as other items in the set? You need a way to deal with that. Well, I've got a formula for this on the next slide that shows you how to deal with this. It looks confusing at first, so bear with me. Okay, the way it works is that what you actually have to do is take the factorial of the total number of items you have, but then you have to divide by each number of unique items on the bottom. Okay. When I had, say, 7 people, let me do a different example. I had 7 people. There were 7 total people. But since everybody is unique, up till now, what you were really doing is dividing by, well, there's 1 U, and there's 1 U, and there's 1 U. You're putting a whole bunch of 1s on the bottom. That makes sense? Because each item up till now we've been talking about is different than the other ones. But let me use manipulatives again here. Okay. So let's say I have all these items here. Let's just go with these 6 items here. You guys see I have 6 items. I've got tape, I've got string, scissors, highlighter, and then these 2 are the exact same as each other, right? I have 6 items. You would think the answer should be 6 factorial. Is that actually different, though? No, it's not. So we need a way to fix that. Now, when all of these items were unique, it was really 6 factorial divided by 1, 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 because each of them is unique. In this example right here, it's going to be 6 factorial divided by 1, divided by 1, divided by 1, divided by 1, divided by what we're really doing is we're getting rid of half the possibilities. If I were to change these two around with each other, it's no different, right? And so wherever those two happen to be there, if I flip them around, I'm actually counting something twice. So by dividing by 2 factorial, I'm getting rid of the repeated possibilities. So I want to go back to this one right here. The way you'd solve this now is that there are 5 total letters. There is 1 U. There is 1 Y, but there are 3 P's. Make sense? And what this will do is this will account for all those repeat possibilities where if I change around the letters, they're the same. Well, now I'm not counting those again. So this is going to be 5 times 4. This should be 20 by the time we're done. Yeah. Does that make sense? Let me show you some more examples like this, and then I'll show you some examples as to where this would matter. Let's try it with these words here first, though. This isn't really purposeful yet. It's just an exercise to practice the concept. Okay. Let's say that I gave you all these letters here in the word scissors, and I asked you how many ways could you arrange them. So first question, how many letters are there total? 1, 2, 3, 4, 5, 6, 7, 8. However, many of the letters are repeats. If I were to change these 2 S's around, would it actually make a different word? No, which means that it can't be 8 factorial. It's going to be much less than that. So there are, I believe, 4 S's, 1 C, 1 I, 1 O, and 1 R. Now, I got to point out, what's 1 factorial? Yeah, 1. So I got to be honest, most of the time we don't bother writing all those ones out. That's kind of dumb. So your final answer would be 8 factorial divided by 4 factorial. Whatever that is. What about in the word Mississippi then? So same thing. Count up all the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 total characters in the word Mississippi, but many of them are repeats. Okay, 1 M. I'm not going to write it. 4 I's. 4 S's. 2 P's. Whatever that is. I should point out, by the way, I should show you this. When you have something like this, be super careful with brackets. Don't type this in. 11 factorial divide by 4 factorial times by 4 factorial. Why is this going to be wrong if I keep doing this? Do you guys know? Yeah. So it's going to take 11 and divide by the 4, but then it's almost going to treat these guys as though they're on the top of the fraction. So you have to make sure that you put this in a bracket here. So go bracket 4 factorial times 4 factorial times 2 factorial. Does that make sense to everybody? Make sure you're careful there, otherwise you'll totally get a wrong answer. Okay, let's talk through what we've learned up till this point here, and then I believe my next slides are a bunch of diploma questions. Is that right? Oh no, I still have one more example, then the diploma ones. Here's actually a good example, this plate one here, of the same thing. You're going to put plates away in the drawer. Again, not that this is overly purposeful, okay? But like I'll find you purposeful stuff later. Okay? You've got, what, 7 plates there? How many ways can you arrange the plates? Well, because there's 3 white plates, they're more or less identical to each other, right? Sometimes I call this the twin problem, where you have 2 people who look the exact same as each other. And if you were to change the order around, you wouldn't be able to see the difference, right? If you change the order of those 3 white plates, who would know the difference, right? So, how do you solve this one? The answer is 7 factorial over 3 factorial. 7 because there's 7 total plates. The 3 factorial is because there's 3 white plates. Technically, there's a bunch of 1s on the bottom as well. There's 1 for red, 1 for yellow, 1 for green, 1 for blue, but let's skip those. Okay, now let's do my summary. Here's what we've learned so far. A bunch of theory, more or less. Your biggest struggle is how to apply it. Fundamental counting principle. If you're trying to do multiple things, and this has to occur, and this has to happen, and this has to happen, you need to multiply. If this has to happen or this has to happen, you need to add. Okay, so there's one of the first things you need to know. Okay, it's usually at some level really basic. You just need to multiply numbers, but there's a few twists you need to be aware of. Like for example, if you use something, can you use it again? Because sometimes it could be 4 times 4 times 4 times 4. But sometimes you can't logically use it again. So then it's 4 times 3 times 2 times 1. It's going to be your job to figure out which of those two scenarios is correct. Another possibility, maybe you don't use everything. Maybe there's 10 items and you use 3 of them. So then it would be 10 times 9 times 8, and the remaining ones don't get used. I've shown you some shortcuts about how to write that. There's also little twists like, well, what happens if these ones have to be next to each other? Or what if they can't be next to each other? Or what if they look the same as each other and they're identical? So those are some of the twists we're going to come across. For the next little while here, let's go through some old diploma questions. These are off old diplomas. Let's see whether we can now build these skills. And one of the things you're going to either love or hate about them is that it literally is just look at the problem, and it's like a 30-second or less calculation probably, but you have to understand the scenario. So here's the first one. You got 5 light switches. The question basically is, how many ways can we arrange the 5 light switches? So let me give you some, let's not look at the answers here, let me give you some possibilities. Maybe you can pick out which one is right. One possibility might be saying 5 times 5 times 5 times 5 times 5. Okay. Maybe you think the best answer is 5 times 4 times 3 times 2 times 1. Maybe you think the right answer is 5 times 2. Maybe you just think the answer is 5 because that's actually right on. Maybe you think the answer is 2 times 2 times 2 times 2 times 2. There, I wrote a couple of things that each one of those is an answer to a different type of question. Our goal now is to figure out which one of those is the right one. Any thoughts? 2 to the power 5 is right, yeah. Because what you were really given was 2 choices here, 2 choices here, 2 choices, 2 choices, 2 choices. Now, just because this one is on right here, does it mean that this one here can't be on as well? No, right? They both can be set in the on position. So it's not like it has to go 5, 4, 3, 2, 1. This is the sort of thing where you can repeat the same number over and over again, right? Once you turn this one into the on position, there's no rule that says that, well, now the next one can be. So this was 2 to the 5, which was 32. Make sense? You have to think of these as puzzles, because that's really what's happening in this section. You got to interpret the puzzle. Next scenario. A couple is going to have a baby, and they're trying to figure out who to name it. So here's what they've narrowed it down. This was totally me and Melissa, by the way. If it was a girl, they've got 3 name possibilities for the first name, and then 2 possibilities for the middle name. If it's a boy, they have 3 boy names, and then 3 boy middle names. Long story short, with all of this information you have here, tell me how many ways you can name the possibilities for babies. You just feel like you understand the scenario first. Because first you have to wrap your head around what I'm asking you. Does anybody not get the scenario? Okay. So let's start to walk through it. You have a name, right? You have a first name, and then you have a middle name, and then you have a last name. How many first name possibilities were there if it was a girl? Okay. Why should I put a times there? Because you have a first name and you have a middle name. It's not you have a first name or you have a middle name, right? You have a first name and you have a middle name. How many middle name possibilities were there for a girl? Okay. And then it kind of implied this one, but how many last names are they probably going for here? Yeah, they probably have one last name figured out, right? Now, this is if you have a girl, though. This is if you have a girl. Or you could have a boy. Right? You can either have a girl or you can have a boy. Well, then for the boy, you have the same sort of logic here. For the boy, there were 3 first name possibilities they had picked out. There were 3 middle name possibilities. I think it kind of assumes that there was 1 last name. So if you were to do this, 3 times 2 times 1 would give you 6. 3 times 3 times 1 would give you 9. What should you do with those 2 numbers, though? Yeah, add them, make it 15. But let me show you how they come up with some of the distractors. You guys see how there's 54 right here. 54, that's because 6 times 9 gives 54. But that doesn't make sense because you either have a boy or a girl, right? I mean, they didn't say you were having twins, right? But, I mean, there's another twist. If it was twins, well, that changes everything. Another one of them here, I think, would have been like, this is 3, this is 2. 3 times 2 would give you 6, or 3 plus 2 would give you 5, and then 3 plus 3 here would give you 6. 5 times 6 gives you 30, or 5 plus 6 gives you 11. You guys see where they came up with some of the distractors from? Which is cruel, because they're going to come up with logical mistakes, and they'll be like, well, rather than multiplying the numbers, then let's add them instead. That's your biggest struggle. Okay, here's another one. You are working at a security company, and you have to type in a security passcode. So the letters you're going to use are the vowels A, E, I, O, U, and Y. And it gave a little thing that's really important here. It said, no letter may be repeated, though. You guys see that little thing right there? So once you use the letter A, no more using A again. Now, this is a really unique kind of question, though. They say, well, let's add the letter G to the list of letters. They've even bolded this word here. The question is, how many more codes are possible? So what we really have to do is figure out how many codes originally were possible, then find out how many codes are now possible into the new parameters. And once we find those two numbers, we need to subtract them. Yeah, we're going to find out how many there originally were. Let's say there were 5. And then you upgrade it, and now there's 10 available. Well, 10 minus 5 means there were 5 more. So let's try this first. Originally, there were a 3-letter code, right? And you had 6 possibilities. But then once you use the letter, then there's only 5 possibilities, then there's 4 possibilities. This is what there originally was. So 6 times 5 times 4, I believe, is 120. Make sense? Okay, now under the new parameters, you still have a 3-digit code, right? But now how many letters are available? 7. But once you use that first letter, then there's only 6 left, and there's only 5 left. And I believe this is 210. So you used to have 120 codes. Now you have 210 codes. How many more codes were there? 90. Some kids love this stuff. They're like, this isn't bad, right? Because it's so different. There's no work. Right? Like compared to algebra, where you're doing all sorts of writing for x, or functions, where you're graphing stuff like crazy, this is all really about, do you get it? And this is what I hate about it, because I can try to give you guys lots of help and examples, but at some point, like, either you get it or you don't. It's just kind of harsh. Oh, what is it? Okay, another possibility here. Like I said, these are all old diplomas. So,
Randy Bonnet, can you please come to the office? Randy Bonnet, please come to the office.
Okay, so grad council is trying to put together a menu, and you're basically going to select one thing off of each list. By the way, eventually here we're going to have to talk about, well, what if you can select 2 things off of a list, 3 things off the list? We haven't got that far yet. We're just going to say, let's just select 1 salad, 1 main course, one of everything. Make sense? Well, if it's just one of everything, then for salad you have 4 choices, it looks like. Main course you have 3 choices. Side dish you have 5 choices. Vegetable you have 5 choices. Dessert you have 4 choices. What should I do with all these numbers? Yeah, the answer is multiply them. Yeah, because you have to pick a salad and a main course and a side dish. Now, for this question, they were super nice because it was pick one of each. Do you guys get what I'm saying here? What if you're allowed to pick 2 main dishes? How does that change things? We have to find a way to account for that later. Anyways, anyone to calculate this? 4 times 3 times 5 times 5 times 4?
1,200.
So 1,200? That number there? Cool. All right, next one. No, that's it actually. Okay. You guys don't have these notes in front of you? Who would need them? Okay. Because I would like to at least start it, because that thing I just described there, where you can take 2 things, your hands up again. 1, 2, 3, 4, 5. I'll go 6. Throw it out of the middle school printer there and see what they're showing. Okay. Okay, while he's grabbing those here, I think I can start talking about the first couple of examples here. We'll just fill in the math when he gets back. So I want to present 2 scenarios to you here. Okay. The first scenario here, you got 15 kids coming to Kinsey's birthday party. And what we're going to do is we're going to give out some prizes to some kids. Okay. In one case, it's a stuffed animal, a gift certificate, and a DVD. And then in the second scenario here, it's very similar in terms of how the math's going to turn out. We've got 15 kids who are going to be on a grad committee, and we want to have a president, a vice president, a secretary, and a treasurer. Let me show you how we can solve both of these ones here, and then I'm going to show you a new notation here. For this one right here, really there's 3 prizes, right? There's 1, 2, 3 prizes. Here's the stuffed animal, here's the gift certificate, here's the DVD. Okay, so there's 15 kids available to give a prize to, right? So 15 kids could win the stuffed animal. Once the kid wins the stuffed animal, we take their name out of the box, right? That's only fair. So then how many kids are left to receive the gift certificate? 14 and then 13. And I've already shown you this. There's a faster way of writing this. I want to train your brains to think of this. There were 15 kids total. 3 of them got a prize, but really there were 12 of them who did not get a prize. Think about it this way here. You know how we talked about that plate example where there were like 4 white plates or 3 white plates and a bunch of different ones here? In a way, here's a better way of writing it. There were 15 total kids there. 1 of them got the first prize. 1 of them got the second prize. 1 of them got the third prize. Grab the door for Darian. And then all of the kids who did not get the prize, effectively they're the same as each other, aren't they? They're all the white plates that are the same. And so 12 kids did not get a prize. 1 kid came in first. 1 kid came in second. 1 came in third. And 12 kids tied for last. Say that one more time. This is actually something we've already talked about here. The 15, 14, 13 could be written as 15 over 12. But the reason why it's 15 over 12 is that 1 kid gets the stuffed animal. 1 kid gets the gift. 1 kid gets the DVD, and the 12 kids who don't win, they all finished in a tie for 4th. Let me try the next one with us. Similar sort of concept here. You've got a president, you've got a vice president, you've got a secretary, you've got a treasurer, and there were 15 kids to choose from. This time around it's a bit different because there's 4 positions, but the math is pretty similar here. 15 kids could have been president. Once someone's elected president, then there's only 14 spots left for vice president. Then there's 13 kids left for secretary, 12 left for treasurer. This is like that sports analogy I gave earlier. We've got cuts here, right? How many kids didn't make the team? 11. Right? So in a way, you could say this is 15 factorial over 11 factorial. Or think of it this way here. There were 15 people. The first place person, there's 1 of. The second place person, there's 1 of. The third place person, there's 1 of. The fourth place person, there's 1 of. And then everybody who lost, really they're all the same as each other, right? Does it matter whether you were in 5th or 9th? Well, in this context right here, it doesn't really matter, right? Like, you either got one of the 4 positions, or everybody else, you're on your own. Does that make sense there? So really, I'm showing you the exact same thing we've learned before. Make sense? I don't remember for the life of me why I have this second slide on here about coffee cups anymore. I used to have a point for it, and I've forgotten what it is, and I should really change my notes. But I think it had something to do with the idea of, like, this is back to being about arranging items. You know, like you could, when you get your coffee, you could get just espresso or espresso and foam. But like this is the number of unique ways you can make a coffee. I don't remember what my point was. So I'm going to go past it. come back to, I want to talk about this slide here, and then hopefully, is it my next one I've got it there? Bah, never mind. I take it back. Can you guys find this slide here first? Then I'll skip back to the other ones here. I think I'm ready to make the point with the formula here. It is very, very common to have a scenario where you write it like this: 8 times 7 times 6, and you stop. And then really what you've got is 8 factorial over 5 factorial. This scenario is so common that we've actually pre-programmed a name and a function in your calculator for it. We call it a permutation, where basically you have a certain number of objects and you take some of them. But you only take some of them, you don't take them all. For example, in one of the last ones we did there were 15 people, and 4 of them got to win. Does that make sense? There were 15 people, 4 of them got to win, which by the way meant that like 11 didn't win. Well, this is kind of the formula we just used there, where we said we had 15 factorial, and we divided by 15 minus 4. What's 15 minus 4 though? Yeah. Which is why we just wrote it as 15 over 11. It's so common to have this scenario, there's actually a button in your calculator. So let me show you this here. You know how we did 15 times 14 times 13 times 12 gives this answer right here? Here's a faster way of doing it. There's 15 people. Go to Math, go over to PRB, and go pick the second one. When I refer to this, I call this picking something. So I'm going to say that there's 15 people. Let's pick 4 of them to win. The reason why we're picking 4 of them to win is that there were 1, 2, 3, 4 slots. And this is like a faster way of getting the same answer. It's such a common scenario that we give it a name. We call it a permutation. So if I could go back, I want to show you how to do the first slide there again, a little bit quicker. There were 15 kids here. 3 of them win. Call it 15, pick 3. Here, there were 15 kids. 4 of them win. Call it 15, pick 4. Makes sense? It's a shorter way of writing down such a common idea. I was going for something like that on the coffee slide, but I don't remember anymore. But I think I remember what I was going for here. On this slide right here, this is all about that ways that we can arrange the letters. How many letters do we have right here? How many letters am I actually going to use when I make the word? It's actually possible to do something like this. 3, pick 3. Let's have 3 letters to start with, and let's pick all 3 of them to be used. Try that in your calculator. What is 3, pick 3? 6. Watch. There were 1, 2, 3, 4, 5, 6 ways to take 3 letters and use them all. Here's another example here. There are 3 chairs, and what I want to do is I want to use 2 of them. There are 3 chairs, and I want to use 2 of them. Well, this would be 3, pick 2, which actually, by the way, happens to be 6. What? Let me show you why. This is a really useful note here. 3 pick 3 was equal to 6, and 3 pick 2 is equal to 6. Let's prove it why. 3 pick 3 means this. There were 3 people. How many of them didn't get picked? You have 3 and you pick all 3. How many didn't get picked? Okay, I'm going to divide by 0 then. Right here, 3 pick 2. How many people didn't get picked? Okay, that's how this works. Now, 3 factorial means 3 times 2 times 1. And there's a rule that basically says if you ever have a 0 factorial, it's equal to number 1, because you can't ever divide by 0. So that's 3 times 2 times 1. Well, right here, this is really 3 times 2 times 1 divided by 1. And normally you'd cancel out those 1s right there. But isn't 3 times 2 the same as 3 times 2 times 1? So kind of a weird little anomaly, but sometimes the answer is actually the exact same. You could have 3 and pick 3. You can have 3 and pick 2. It's actually the same number. Weird. The reason why I want to talk about marble slab then is we now need to start talking about the idea of, let's say that you go and you want to make your ice cream cone. Do you have to have just one topping? No. This is a good example of a pick scenario there, where there are 10 toppings and you could say pick 5 of them. That makes sense? We need to incorporate this sort of logic in to our problems now, where you don't just have to have one of everything. You could have 2 out of 5 kinds of ice cream. You could have 3 out of 7 types of toppings, and like 1 out of 4 types of cones. So sometimes we're going to need to use pick when we solve our problems. So let me try some more examples here. Scroll ahead. Phil is going to try to buy 6 songs off of iTunes out of his favorite 10. After a while, this actually gets super easy then. There are 10 possible songs. He wants 6 of them. So the answer is 10, pick 6. That makes sense? Now, other ways of writing this, just so we're clear, you could also have written this as 10 times 9 times 8 times 7 times 6 times 5. That also would work. You also could have written this as 10 factorial over 4 factorial. The 4 being the 4 songs that don't make the cut. Any of these 3 things here all equal the same answer. I need you guys to be familiar with any of them. I had a slide here just to remind you that, like, where does this get used? Security. Right? Anything involving security usually involves numbers of combinations. So. Okay, let's try this next couple ones here, and then maybe I'll do, what do I want to get to? Okay, I'll go all the way up to this slide right here. I'll end before we get to this slide. Is that fair? So give me 1, 2, 3, 4 more slides. Is that fair? Okay. So you've got the letters in the word graphite. I want you to make a 3-letter arrangement. This is actually really easy now. There's 1, 2, 3, 4, 5, 6, 7, 8 letters, and you need 3 of them. That's it.
Wait, how many?
I believe there's 8 in the word graphite, right? And it said they can only be used once, right? So really you had 8 times 7 times 6. Or this could be 8 over 5, each with a factorial. But what I'm trying to show you guys right now is this is the faster way of writing it. Just write 8, pick 3. Here's another one here. In South Africa, the way they make vehicle license plates, they give you 2 letters and then 4 digits. But the rule is that once a letter is used, it can't be reused. How many letters are there in the alphabet? How many of them are you going to need? 26, pick 2 is the letters. Now, for the numbers, it didn't say anything about numbers, though. It said 4 digits. So how many digits are there? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. But I want to point this out here. This is not going to be 10, pick 4. Because it didn't say that you couldn't reuse the numbers. If you couldn't reuse the numbers, it would be 10, pick 4. But if you can reuse the numbers, it's 10 to the power of 4. Does that make sense? In one case, it's 10 times 9 times 8 times 7. But in the other case, it's 10 times 10 times 10 times 10. Right? You got to be really, really, really careful about whether or not things can be reused. If it can be reused, it's not a pick scenario. Because by definition, once you pick something, it's been used. So one more time. If you can reuse it, it's not, don't use something, pick something. Don't use that pick notation. Because once you've picked it, by definition, it's now out of the running. The numbers always have to go 10, 9, 8, 7 and get lower. But if you can reuse it, then go to the power. So the final answer here would be like 10 to the power of 4 times by 26, pick 2. This would be a good way of writing it. There's 4 digits, 10 to the power of 4, 26, pick 2 for the letters. What if we had 11 people on the soccer team and we wanted all 11 in the photo? Yeah, it is valid, by the way, to do 11, pick 11. You can't have everybody get selected. But I think I made this one to make a point here. It's not valid to do this. That's physically impossible. Why? Yeah, you can't pick more than you start with, right?
Like you eat 7 pieces, repeat 7. There's only 6 pieces
Exactly, yeah. You have a limit, right? This number right here, this is the biggest number it can be. And it has to be whole numbers. You can go 11, pick 0. You can go 11, pick 1. You can go 11, pick 11. But here's some things you can't do. You can't go 11, pick 4 and a half. There has to be whole number increments. You can't go 11, pick 95. You can't have more than you start with. Okay. But you can pick as many as were totally there. You can even pick 0 of something. Okay, this was my last slide I said, right? 2 more slides. Okay, you have a social insurance number. Okay. The way these ones work in Canada is it's a 9-digit number, but I want to point out there are no restrictions on the digits. So if you have a 9-digit number, it's really 10 to the 9. Because there's 10 choices for your first digit, 10 choices for your second digit, 10 choices for your third digit. It is not 10 pick 9. That's what you wrote at first?
9 to the power 9.
You're close. It's 10 to the power of 9 because there's 10 digits that you can use 9 times each. But do you guys get the point I'm trying to make here? Don't use pick if you can reuse it. Pick, by definition, implies that it has to get lower every single time. All right, last one, then we'll go. Okay, we're going to play some sort of Scrabble kind of game. Apparently the way this works is that we're going to try to spell the word Canada. And we're going to try to rearrange the letters, and I'm going to tell you the first letter has to be N, last letter has to be C. I don't know why, but that's the rules. Fine. How many letters are left over? 4 of them are left over, right? How many of them do you need? Actually, we need to use all 4, don't we? But this now is going to combine what we've learned with what we did in the last lesson here. Do you guys see how there's 3 A's? So we're still going to go 4 pick 4 because of the 4 letters that are left to be left over, right? You need all 4. But because 3 of them were A's, we still have to divide by 3 factorial. We can combine stuff still. Make sense? I believe the answer to this is actually 4. 4 pick 4, but then divide by 3 factorial is 4. To end off class, why don't I just draw those ones out for you? You can see whether you agree here. I believe I have 3 A's and a D left. It could look like this then. A, D, A, D, A, D, A, or D, A. You guys see how those would be the only 4 ways you could do this?
You got like a D.
Yeah, and you can almost like see the diagonal as I wrote here. So, last thought here. You should also have the ability to combine some of these skills. So 4 pick 4, sure, but don't forget to divide by 3 factorial because there were 3 A's. Sound good?
Yeah.
Okay, we'll finish this on Monday then. Have a good weekend, guys.
I had